Suppose a factory produces light bulbs and two machines A and B are responsible for producing them. Machine A produces 60% of the bulbs while machine B produces the remaining 40%. Machine A produces defective bulbs at a rate of 5%, while machine B produces defective bulbs at a rate of 3%. If a randomly selected bulb is defective, what is the probability that it was produced by machine A? Okay, thank you so much for being here today with us, Apurva. Can you quickly introduce yourself for our viewers?
Sure. Hi, everyone. I'm Apurva. I currently work as a data scientist in a tech company in the ads team. So, my team's focus is to ensure that our ad quality is high supply. And we also think about how to increase ad revenue while at the same time making sure we don't affect user experience too much.
Perfect. So it sounds like you have a lot of experience with analyzing data on the job, so I'm eager to see those skills being applied today. So our first question today is, suppose a factory produces light bulbs and two machines A and B are responsible for producing them. Machine A produces 60% of the bulbs, while machine B produces the remaining 40%. Machine A produces defective bulbs at a rate of 5%, while machine B produces defective bulbs at a rate of 3%. If a randomly selected bulb is defective, what is the probability that it was produced by machine A?
Okay. So, so reading this question, I can see that it involves calculating conditional probabilities um, because essentially we have to calculate the probability of a certain event given another event. So, keeping that in mind, I think Bayes' theorem is what I would use to solve this problem. So, I'll first start off by just writing the formula for Bayes' theorem. Let me just go ahead and do that. And writing it out this way is what I find the most useful instead of just trying to memorize the formula, because this essentially, um, at least for me, is easier to understand because all this is basically saying is that the probability of joint probability of A and B is equivalent on both sides.
And that's just like the joint probability, but factorized using the chain rule, right?
Yeah. So now that we have the equation written out, now I'll fill in each of these conditional probabilities. So I think there are a few different. So ultimately, the probability that we need to estimate is what is the probability if if we select given a bulb is defective, what is the probability that it was produced by machine A?
Okay.
So essentially, so what we need to find is PD given A, where D is the probability of being effective, or sorry, being defective, and A is the probability that it was produced by machine A.
Okay. Yeah, could
So
we
if
write
we,
out what each of the events are?
yeah, so this is what we need to find out. And in order to do this, we need PA, which is the probability that the bulb was produced by machine A, and that is 60%. So that is equal to zero point 0.6
Do you mind writing out
P.
like what each of the random variables represents, like A, B, and D?
Oh, yeah, sure. Yep. Then PB is essentially 1 minus this probability. So that is 40%.
So that would
And
be
then,
B, right? Probability that machine B produces the bulb.
yeah. Oh, sorry. Yes. And then we know that machine A produces defective bulbs. at a rate of 5%, while machine B produces defective bulbs at a rate of 3%. So the probability of Oh, actually, sorry, I made a mistake here. We actually want to find A given D, because here we know that a randomly selected bulb is defective. So we actually want to find probability that it was produced by machine A given D.
Okay,
We already have PD given A,
can you write out
which
what D
is,
represents?
oh yes. So this just represents probability that a bulb is defective.
Okay.
And we don't have this, so we'll need to calculate this, but I'll do that
Mhm.
once I write out the other probabilities that we already know.
Okay, great.
So we already know PD given A, and that is 5%. I'll write it down. And we also know PD given B, and that is 3%. Okay, so yeah, I think now I've written down all the probabilities that we've been given.
Mhm.
So now I'll first calculate PD, because that's the one probability which we'll need to calculate, and which is needed to calculate the final P probability of A given D. So using the laws of probability, PD, there are basically two possible outcomes here in order to calculate PD, that either the bulb was produced by machine A or produced by machine B. So therefore the probability that the bulb is defective is basically PD given A times PA, which is basically if the bulb was produced by machine A, what is the probability that it is
Uh-huh.
defective, or PD given B times PB. And we already have all of these values, so
Mhm.
I can just plug those in. So PD given A is 0.05 times PA is 0.6 plus PD given B is 0.03 times 0.4. And so I'll just use my calculator to calculate this. But so this comes out to be 0.042. So now we have all of the values needed to calculate PA given D. So I'll just go ahead and do that. So PA given D, if we if we use the Bayes theorem, that'll basically be PD given A times PA divided by so yeah, so here this I basically just plugged in the values into the Bayes theorem formula, And now
Right.
we have all of these individual components, so I can just go ahead and plug those in.
Mhm.
So PD given A is 0.05 times PA is zero point 0.6, and then divided by PD, which we just calculated, is 0.042. And so if I do this calculation, that comes out to approximately 5 by 7.
Mhm.
So yeah, so that's our final answer. So yeah, we just calculated what the probability of, given that a bulb is defective, what is the probability that it was produced by machine A.
Okay, amazing. That sounds perfect to me, Aporva. So let's move on to our next question then. The next question is, what is the p-value?
So I'll first start with the technical definition. Um, so the technical definition of the p-value is it's the probability of obtaining test results or data at least as extreme as the data or results we're actually observing, given that the null hypothesis is true. And a simpler way to explain it is a smaller p-value indicates stronger evidence against the null hypothesis, while a larger p-value suggests that we do not have enough evidence, or the evidence we have is not as strong.
Okay, and you mentioned a null hypothesis. Can you explain what a null hypothesis is?
Yeah, sure. So in hypothesis testing, which forms the basis of A/B testing, which a lot of companies do to try and figure out if the changes they're making are actually having a positive impact on their success metrics. Um, the null hypothesis basically represents a default assumption. So it's sort of like the default state of a product, or of a system, while the alternative hypothesis is basically the claim we're testing. So, for example, if we decide to add a feature, we want to understand if that feature actually improved our key metrics. So, the null hypothesis in this case would be that there isn't any change to our key success metric from this feature, while the alternative hypothesis would be that this feature actually did improve our key metric by some percentage. So, I can talk through a concrete example if you want.
Yeah, that'd be great. But to quickly restate, are you basically saying then that null hypothesis implies that there's zero difference in means between the two groups?
Yeah.
Okay, cool. Yeah, I'd love to hear an example then of how you would use a p-value in practice.
Yeah, sure. So let's say our null hypothesis is that we are comparing the weight of apples from two orchards, orchard A and orchard B. So our null hypothesis is that the mean or average weight of apples from orchard A is equal to the mean weight from orchard of apples from orchard B. And our alternative hypothesis in this situation is that the weights are actually different. So here, when I say different, we're not really specifying the directionality, which means that the mean weight of apples from orchard A could either be higher or lower compared to orchard B. And so then in order to test this hypothesis, we collect a random sample of apples from each orchard and measure their weights. We also essentially we calculate the sample mean as well as standard deviation for both of these samples, and then we can conduct a two sample t-test. So here the reason I said two sample is because or actually not two sample, I think two-sided t-test is because we're not specifying the directionality. So we're just interested in understanding if the mean weight of apples from orchard B is different from orchard A, and that's why we would use a two-sided t-test. So to compare the means of these two samples, and then we would calculate the test, what we call the test statistic, using the mean and standard deviation from the samples we just calculated. So now we finally want to find out the p-value associated with this test statistic. And usually we would just use some statistical software to look up this p-value, but there are also t-distribution tables which you could look at if we were calculating this manually. So in
Okay.
this case, let's assume we find that the p-value is about zero point 0.1.
When you're looking it up in the table for like the t distribution, for example, like what is the value that you're actually looking up, like with respect to that distribution?
So you would be looking for the t statistic value, and essentially each t statistic is associated with a p-value. So you would be looking up the t statistic or critical value, and then getting the associated p-value.
Yeah, so the probability with respect to that distribution, the p-value with respect to that distribution, is that like an area under the curve? Is it like a marginal probability? Like what would you define it as?
Yeah, so basically, you would compare that p-value to a significance level, which is denoted by alpha. And usually, the standard is to set that value to 0.05. So basically, what that means is what alpha of 0.05 means is that if the null hypothesis was actually true, then the probability of seeing the t statistic that you are seeing is 5%. Um, yeah, is 5%, which means it's a pretty low probability that the null hypothesis is actually true. So
Okay.
essentially, what we're doing is we're comparing the the p-value we got from our t statistic to this alpha. If p is the p-value we get from our t statistic is lower than alpha, that means we can reject the null hypothesis. But on the other hand, if it's greater than alpha, that then we do not have sufficient evidence to reject the null hypothesis. And so in this case, the p-value we calculated was zero point 0.1,
Mhm.
which is greater than 0.05, which means we do not have sufficient evidence to reject the null hypothesis, which means that we can't conclude that the mean weight of apples from orchard A is different from the mean weight of apples from orchard B at the zero point 0.05 significance level.
Okay, yeah, so in general, we're failing to reject the null hypothesis in this case, right?
Yeah.
Okay. Yeah, and I guess like one extra point is we talked a little bit about how does the p-value actually relate to the t-distribution, like explicitly speaking, and actually the p-value can be computed from the inverse cumulative distribution function of the t-distribution, right? And that's why like we often look it up in tables instead because it's difficult to compute, right?
Yeah.
Yeah, okay, cool. So moving on, this is also a statistics question. What does the confidence level mean when you're building a confidence interval?
When we make an estimate in statistics, there's always uncertainty around that estimate, because usually in inferential statistics, um, you're essentially whatever estimate you're calculating is based on a sample of the population you're studying. Like you usually don't have the data from the entire population, but instead you randomly sample from the population and then um, make an estimate, whether it's a summary statistic or a test statistic based on that estimate. So basically, there's always some uncertainty around that estimate, and the confidence interval helps us quantify that uncertainty. So the confidence interval is basically the range of values that you expect your estimate to fall between a certain percentage of the time if you run your experiment again or resample the population in the same way. So basically, to use a more concrete example, if you construct a confidence interval, or like say you perform or you come up with a summary statistic, and you say the confidence level or confidence interval for that statistic, say falls between 1 and 5,
Mhm.
then essentially what that means is that if you repeat the test, or if you sample the population, if you randomly sample the population multiple times, then for a certain percentage of time, you would expect the mean, the whatever statistic you were calculating to fall between 1 and 5.
Okay, I see. So then, how would the confidence level affect the width of the confidence interval?
Yeah, so the confidence level is basically the percentage of times you expect to reproduce the estimate between the upper and lower bounds of the confidence interval. So in the example I was just saying, I was just talking about, if you set the confidence level to be, say, 95%, um, then that would mean that if you sample the population 100 times, then 95 out of those 100 times, you can say that the estimate will fall between the upper and lower values specified by the confidence interval. So basically, there's usually a trade off between the confidence level and the width of the confidence interval, because a higher confidence level usually leads to a wider interval, because then we're more certain that the parameter of interest will lie within that wider range, whereas a lower confidence level usually results in a narrower interval. But that also means that we're less confident that the interval contains the parameter of interest.
Right.
So yeah, I can also explain more with a more concrete example. So suppose we want to estimate the average height of adult males in a city. So obviously we can't go and we don't have data for each adult male in the entire city, because that would be very difficult to collect. So instead we take a random sample of around 2000 males and then calculate a 95% confidence interval for the population mean height. So let's say we do that and find that the interval and estimate the interval to be between 170 and 180 centimeters. So the lower bound of the interval is 170 centimeters and the upper bound is 180 centimeters. So here the confidence level of 95% basically means that if we repeat this sampling exercise 100 times, each time with with 2000 males, that means we basically gather 100 samples, or repeat the sampling exercise 100 times. Each time we're taking a random sample of 2000 males, then a confidence level of 95% means that 95 times out of this 100 times sampling exercise that we did, the mean will fall between the 170 to 180 centimeter range.
170 to 180 is your confidence interval for the 95% level, right?
Yeah,
Okay.
yeah. So now let's imagine we reduce the confidence level to 90%, which means that we're okay with being slightly less confident about our results. Then in this case we could potentially reduce the size of the confidence interval. Like now we since now we only need a confidence of 90%, which is lower than 95%, we could say that actually the confidence interval is now between 172 to 180 centimeters, since we've reduced the level of confidence that we want. And conversely, if we want to be even more confident, like let's say we want to be 99% confidence, uh, we want to be at the 99% confidence level, then obviously the confidence interval will need to be larger,
Right.
because then there are cases where, for example, if somebody is at 169 centimeters, like we would still essentially we would the confidence interval would become wider, because now we want to be much more confident. That is, we want to be confident at a 99%. That means we would, for example, want to include uh, males who are also at, say, 169 centimeters or 181 centimeters, because we want to make sure we're accounting for as much of the as much of the population that covers gets us to this 99% confidence level.
Or perhaps it really just covers the variance that it can occur across the sampling
Yeah,
procedures, right?
yeah,
Yeah. Okay. So then, like, the wider your confidence interval, the more likely it's going to capture that variance.
Yeah.
Yeah, okay, amazing. That's our last question for today. Thank you so much, Aporva. I'd love to switch into our interview debrief mode where we're going to analyze this as if we were interviewers ourselves. So I'm curious to hear from you. What do you think went well, and what do you think you would change going forward?
Yeah, I think for the like starting with the Bayes theorem question, I think that like writing down everything and then sort of like walking through each step, I think that went well because then it becomes much clearer for both me as well as the interviewer to understand my thought
Mhm.
process. I think for the other two questions, I feel like I could have been a bit more clearer in both the structure of answering as well as sort of just like the phrasing I was using. Like I feel like it was maybe sometimes a little bit confusing
Mhm.
to follow.
Okay, yeah, that makes sense. I really like though that in general you showed uh, a really deep knowledge of all of these concepts that you explained hypothesis testing, even though I really only asked you about p-values, and you could potentially explain that without delving too much into like hypothesis testing and like null hypotheses and so on, but you were really able to explain all of the tangential concepts really well. And I like that you were able to answer like the follow-up questions about like, well, what happens if you increase or decrease your confidence level and so on. And I really liked your use of concrete examples to explain these concepts too, because I think that really made it more clear. Yeah, I agree. Sometimes for clarity, it can help to explain what your variables are before your calculation. So, for instance, when you were saying that, okay, we need to calculate P of D given A, I actually didn't know what D was yet. So it just helps to just explain what all of those random variables are first. Um, yeah, and I think I was trying to ask about like what the explicit relationship between the p-value and the like t distribution is, because you mentioned like, oh, we use this lookup table, right, to get to look up what the p-value is based off of the t statistics. But what exactly is that lookup table doing, right? And the answer was basically it's using the inverse CDF of the t distribution. Um, yeah, and other than that, I really thought you did a great job, and we've learned so much from you today. So thank you for being here.
Okay, thank you.
Yeah. Okay. And thanks everybody for watching. If you have any upcoming interviews, good luck. Bye, everyone.